Hi, I am Rhea Gordon with the Madison Conservation District, and today we're re-recording a presentation that was given on August 30th as part of the Madison Watershed Speaker Series. So today we have Adam Sigler. He is the Montana State University Water Quality Extension Specialist, and we're going to talk about insights from over 10 years of volunteer collected water data in the Madison Watershed.
Great, thank you, Rhea. Yeah, so happy to have the opportunity to talk, and it's September 22nd, so coming up a couple weeks after this original talk on the 30th, where we had a really nice turnout there at the Ennis Library and had some good discussion too about this. So happy to have this shared in a way that can reach some more folks. But so going to talk about insights from 10 years of volunteer data collection in the Madison by the stream team. And I'm, as Rhea said, the water quality specialist with MSU Extension out of Bozeman, and work to provide technical assistance to groups across the state that are doing volunteer water monitoring, and have been doing that since around 2009 or so. And today we'll talk a little bit about the beginnings of the Madison Stream Team and a broader context of water quality in Montana, and then a little bit about what has been monitored. We're going to focus today on nutrients and on sources and solutions. We'll talk a little bit about where monitoring has occurred, which is primarily in the tributaries, an overview of the fieldwork that Ray is going to talk about, tributary blitz results from the last few years that Ray will focus on, and then a deeper dive into some of the past data and natural versus human sources, and then touch on the watershed restoration plan. So back in 2010, we had our first training, and so Sunny Heikas-Napton, the watershed coordinator at the time, had just finished her master's degree in our department here in Land Resources Environmental Science at MSU, and was getting her feet under her with the Conservation District in Madison County. And so she had some interest locally from people who wanted to collect data, and so we started by creating this map of what was currently known about water quality impairment in the Madison at the time. So a list of the streams with this map and then what they were impaired for, and this ran in the Madisonian in the newspaper with an advertisement for this training that we had. One day inside and then a second day out at the pavilion using hands-on meters. We used in this first year some pretty simple meters, this little handheld specific conductance meter, and these kits for making some estimates of nutrient concentrations. And then things went really well, and so the next year people were enthusiastic and came back out, and so the quality of the work was able to escalate quickly. We bought some more sophisticated meters that can collect better quality data. We started working with certified laboratory to collect samples and have those analyzed for nutrients to get more robust concentration numbers. And in this picture you can see we were still using the float method to estimate discharge in that second year, but subsequently got a Marsh-McBurney flow meter to get more robust flow measurements. So that is the beginnings back in 2010-11. And so if we zoom up to the state level in Montana and we want to start trying to understand water quality, first we have to understand what is high quality water. We need the context of what the water is being used for. And so we see here the list of everything in the state that we want to use our water for. And one thing that is we can notice from this is that we've got both cold and warm water fisheries on this list. And if I ask you, do you think that we can have habitat for both cold water and warm water fish in the same place at the same time? This should kind of highlight for us that no, we can't have that. And so we expect to have different water quality in different parts of the state based on what was there naturally. And so we need to know what these natural conditions are. And if we look across the state, the Montana Department of Environmental Quality has this pretty coarse classification system where there's a number and a letter, and the numbers can kind of roughly correlate with temperature, and the letters in a rough way can correlate with salinity. And on the western half of the state, we have a lot of naturally cold and low salinity streams, and on the eastern half of the state, we have a lot of prairie streams that are naturally warmer and higher in salt. And so just this recognition of the fact that we have very different water qualities in different places is really important if we want to understand natural variability before we can start to think about what human causes of issues are. So once we have that context for what we expect naturally, we can start to look at what the human causes of impairment are. And so here's a list of the Montana Department of Environmental Quality has split the state up into around 1,000 assessment units, and almost half of those are impaired for one thing or another. Sediment is at the top of the list. We also have some metals here, which are a nod to Montana's mining legacy, and then nutrients, nitrogen and phosphorus, which can come from a variety of sources. Animal waste, any animal waste, so humans are animals, so wastewater treatment plants and septic systems, or places where we have a lot of livestock in one place. And we'll also talk a little bit more about some other sources for nutrients as well. And so here are the known causes or sources of these impairments across the state. So we've got grazing is on the list with down here at the bottom, and that shouldn't be a surprise just because we are a very rural state, and grazing is a very widespread practice across the state. We also see things on here like roads and a little bit of forest practice. Notably absent from this list is any point source. All of these most important sources are non-point sources. And this is, we're in a place in Montana where more than 90% of impaired stream miles are from these non-point sources. So this is an important concept that this is a picture of the Cuyahoga River burning back in a Time magazine article in 1969 made famous as the river that oozes rather than flows. And so these point sources are what was dealt with first under the Clean Water Act, starting back in 1972. And these are classically water dumping into the stream from a pipe, and one example is a wastewater treatment plant. And we've made a lot of progress with these, and to a point where now, again, it's all these non-point sources that are things like runoff from our cities, septic systems, runoff from roads, and various agricultural practices that are spread out across the landscape. We are all contributing to non-point source pollution. And there's an important distinction that while the point sources were dealt with under a permitting system under the Clean Water Act, all of these non-point sources are dealt with under a voluntary structure, where if we want to address these issues, we have to, people have to do it voluntarily. And so these non-point source issues they're harder to characterize. We can test the water coming out of the pipe and then follow it back up to the place where it's coming from and be pretty direct about that. Non-point sources are harder to quantify. They often come in through groundwater or during storm events, and again, we're all contributing to this. So there's a lot of information on what these impairments are across the state available from Montana DEQ that I want to highlight. You can go and explore this through this interactive map on their website and pull that up, and all of the stream reaches that have been assessed are on here, and you can see what the impairment category is, and there's a couple of different ways to search on this website. So a wealth of information there on the DEQ's website. Another great source of information is the USGS and their gauge data. So just to talk about the fact that the stream team data is really to complement these other existing data sources. And so just highlighting that the discharge data that USGS has on the Madison River and the temperature data is very valuable. There's some chemistry data in USGS, not so much, although Northwest Energy has a lot of data collection on the main stem of the Madison River. All of the data that I will show you today is available in the stream team data is available in our data hub. This is on my website, and if you click here, then it will bring up this interactive format where you can select which watershed or streams or even specific sites you want to see data for. You can select the date range. This y-axis, if you click on it, is interactive, and you can select different parameters, and then you can select different styles of plots up here. So a lot of information here, and you can interact with all of this data through that website. So yeah, here's changing that from to a time series plot from that box plot. So yeah, you can go explore any of this data that I will present today on your own. So what has been monitored over the years? There has been field parameter data collected, which is temperature, pH, dissolved oxygen, and specific conductance, an estimate of salt. Those things are measured in the field with a meter. Lab analytes, those are things you collect a sample and send it to the lab. Nutrients have been a primary one there with nitrogen and phosphorus, and then metals. Flow, measured in the field, and then data loggers that stay in the stream and make measurements perhaps every hour, and commonly do water level that can be used to estimate discharge, and then water and air temperature. Today we're going to focus in on nutrients, a little bit about metals, or more specifically arsenic, metalloid, and then a little bit about discharge, and then we'll show a little bit of water and air temperature data at the end. So nutrients, why do we care about nutrients? They're beneficial. We buy fertilizer and apply it to our lawns, right? So they provide a lot of benefits, and more importantly, perhaps they provide benefits for us growing food. If we look at the composition of a plant, 95% of the biomass is made up of carbon, oxygen, and hydrogen that the plants can get from the air and from water. If we look down the list of the top atoms present in a plant, nitrogen, potassium, and phosphorus are at the top of the list. And those NPK are the things that we commonly see on the fertilizer label. Today, we're focused on nitrogen and phosphorus, and nitrogen is often one of the biggest emphases. And interestingly, we are breathing right now 78% nitrogen. So it is very abundant in the atmosphere. But all of that nitrogen is in the form of N2, this tightly bound triple bond nitrogen that is not available to life except for legumes and other nitrogen fixing plants, until this gentleman, Fritz Haber, came along in the early 1900s and figured out that if we put the atmosphere under heavy pressure and temperature, we can fix that nitrogen out of the atmosphere into reactive nitrogen, into ammonia fertilizer, to a point where on this plot you can see that we have population increase here over the last 150 years or so, and moving somewhat in parallel with that is the global rate of fertilizer application, to a point where now more than half of the world's population is fed with food grown on Haber-Bosch nitrogen. So this has been huge for this availability of nitrogen for us to be able to feed a growing population. But what is a side effect from that is that we fix this nitrogen out of the atmosphere, we mine phosphorus out of these big geologic deposits, we then collect those and move them around the country to our farm fields and apply those to grow food for us and food for livestock, and then we eat that food and we pass through a lot of the nutrients, the nitrogen and phosphorus, into water, is where we dispose of our human waste in the United States. And similarly, the livestock pass through a lot of that nitrogen and phosphorus into their manure, and that then becomes potentially a contaminant source for water. So there are these inefficiencies in this nutrient cycle that ultimately end up getting a lot of this nutrient into our water. And so for the same reason that we apply nitrogen and phosphorus to our lawns and to our crops to make them grow better, when that nitrogen and phosphorus gets into a stream, that algae or the in-stream vegetation that is typically limited by nitrogen and phosphorus can really take off. And that's when we get eutrophication. Reduced dissolved oxygen. So that's an interesting one that is related to nitrogen and phosphorus. If we look at this really green stream right here, that green means that there is a lot of photosynthesis happening in that stream. And so that means that oxygen is being produced. So why do we have reduced dissolved oxygen? It's a little bit counterintuitive. And the reason is, so we see a pattern in most streams where dissolved oxygen goes up and down like this on a daily basis. And during the day when these plants are photosynthesizing, the dissolved oxygen goes way up. But then at night, the plants are respiring, the fish and all of the bugs are in there using oxygen, breathing, and that oxygen level crashes at night. And when there's so much biology in there, there is a lot of respiration that happens at night, and you get these dissolved oxygen crashes. So it's important to have this, that we go out and measure dissolved oxygen often in the day. That is not when the highest risk time for low dissolved oxygen is. That's right before the sun comes up is when the DO gets the lowest. And so these highly productive streams get these big oxygen fluctuations. And this can cause recreation impairment, both because people don't want to recreate in a stream that looks like that, and it can cause degraded conditions for ecosystems and for fisheries, which can have economic benefits. And there are other types of impacts as well, with potentially harmful algal blooms in lakes and things like that. So a number of issues with nutrients. So what can we do about it? With these different sources, we've got runoff from city streets. We might think about infiltrating water on site. So there are permeable pavers, there are rain gardens, there are rain barrels that you might use, or detention basins if we're thinking about this at the scale of a subdivision or in a city. So a lot of things that you can do to reduce the amount of runoff. If we're looking at runoff from roads, you could think about resloping or regrading these surfaces to reduce the amount of runoff, or you could add vegetative buffers along the edges of roads. With septic tanks that recharge groundwater with wastewater that's treated but still has a lot of nutrients in it entering the groundwater through the drain field, we can look at pumping septic tanks as a basic piece of maintenance. We also need to look at hooking up to sewer wherever possible. So new developments, always going to be better, if possible, to hook up to centralized wastewater treatment, because then that centralized wastewater treatment can be more effective at reducing nutrients and can be enhanced over time as the technology improves, rather than having so many individual septic systems needing maintenance. For fertilizer application, we can think about things like nutrient management plans with considering the application timing so that the fertilizer is being added in the quantities and at the time where the crops need it the most. Agricultural producers have to pay for fertilizer and they want it to get into the crop and not into the water, and so there are some practices like this that can help with that. Legumes are another opportunity with farming-based agriculture where legumes fix their own nitrogen, so you don't need to fertilize them with nitrogen, which is a great opportunity for nitrogen efficiency. And with grazing, we can think about rotational grazing to get better use of forage on the landscape, and we can also think about riparian pastures and buffers. And related to that, here is a study that I was involved in with some agricultural producers and the Natural Resource Conservation Service more than 10 years ago now, and where these animals were initially watering directly in this stream, and so came in, put in this fencing and some off-stream water, and then riparian vegetation grew in, and we had created this runoff event before the project, where it looked like this, and this gray area, this is time on the x-axis, and nutrient concentrations on the y. The gray area is the precipitation period. So once it started raining, immediately there was runoff and nutrients were entering the stream. Total nitrogen and total phosphorus here. After the vegetation grew, we did the same event and a similar event, repeated it, and you can see that with precipitation, there was no runoff into the stream. Just illustrates the fact that vegetation can be a very effective filter for infiltrating water and filtering out nutrients and other sediment and things like that. So where has monitoring occurred? Moving on from what has been monitored and what to do about those things to where. This is a list of all the tributaries, all of the streams that are in the data hub currently, and these are all tributaries to the main stem of the Madison. And so why has the focus been on tributaries? Well, there is monitoring from Northwest Energy on the main stem, and USGS is one thing. And if we think about the importance of tributaries, if we think about putting a practice in here next to a stream that's of a size like this, the opportunity to be able to affect that water quality when you've got a lot of bank relative to how much water, a lot of land use relative to the amount of water, you can expect that changing a practice here can affect the water quality in that stream. Whereas if you, for an extreme, think about the Mississippi River, which can be approaching a mile wide, do you think that same change in practice here on the bank is going to have the same effect on a river this big? No, the water quality for a river this size has already, the trajectory has been set upstream on these small tributaries. If we look globally, something like 80% of the total stream miles are these first order streams, where these are the smallest streams. And those are the places where you have the most potential to affect water quality in the downstream, larger streams and rivers that a lot of us tend to care about as far as fisheries and recreation. So as we look across Montana at the more than 60,000 miles of perennial streams and rivers, we have to think about managing the small streams if we want to have an effect on the water quality in the bigger streams and rivers. And that's really important from thinking about the water that we send downstream to 3 different oceans in Montana. We're a headwater state, and we send water to the Pacific Ocean and to the Gulf of Mexico, and also a little piece up to the Hudson Bay from the St. Mary's up from Triple Divide Peak and Glacier. So critical to think about water quality on tributaries as the beginning of this system. And with that, I want to turn it over to Rhea to talk about volunteering in the field, collecting data in the field with volunteers.
So Adam, at the beginning of the presentation, talked a little bit about the beginnings of the Madison Stream team. And so from that, you can gather from the very beginning, volunteers were an essential part of the program, and they've continued to be until now. Here we have a couple of photos. The center is from our training earlier this spring, beginning of the 2022 field season. We have a couple of volunteers on the left estimating discharge in a small tributary, and then on the right from our tributary blitz collecting nutrient samples. And here are just a few more photos of volunteers out in the field, and the volunteers really are they're hugely committed. They're a great source of experience and knowledge. And it's a great way to get feedback on the program too. So we really rely on them and appreciate all of the work that they put into it. And it's made for a pretty resilient program, having that longevity of volunteers sticking around season to season.
Next slide.
And then in addition to that, we get to go out to some of really beautiful places within the Madison Valley and the Madison Watershed, just from all the way from the Reynolds Pass area, the top right photo at Mile Creek, to up at Jack Creek doing winter sampling down on the bottom at the right. So it's really fun to go out in the field with the volunteers as well, spend some time outside and just hang out. So one of the, in addition to our regular weekly field monitoring of the important tributaries, we also do the Tributary Blitz, and it's an annual sampling event that started in 2020. And we sample 16 tributaries in one morning with the goal of kind of creating a snapshot of the Madison watershed. It's a form of synoptic sampling where you're doing all of the sampling within a small window of time to try to remove variables that change day to day or throughout the day, like weather or other environmental factors that are kind of constantly changing. So this sampling event is mostly focused on nutrient samples. We do take just kind of baseline other water quality metrics such as pH, dissolved oxygen, temperature, and conductivity, but our main focus is on phosphorus and nitrogen. So we only have 2 years of data so far, the 2020 and the 2021. We just completed the 2022 Tributary Blitz at the end of August, but we don't have the results back from the lab yet. So our trend analysis over time is somewhat limited, but it does provide a pretty valuable snapshot, and you can kind of look spatially across how those nutrient samples are coming back from the lab. So this figure outlines our 2021 Tributary Blitz samples. It's our most recent Tributary Blitz event that we have results back from. At the top, we have our total nitrogen, and then on the bottom, the total phosphorus. I've arranged the tributaries from upstream to downstream. Upstream is on the left, and then moving downstream to the right. So you can see the upstream tributaries aren't showing any issues in nitrogen or in phosphorus. And then as you move downstream, we have more tributaries that are going above that threshold. And these thresholds, those dashed lines, they're set based on what would be a natural and acceptable level in this region of each of those nutrients. And you can see that there are a couple that are either high in one and not the other. And then there's also a couple 8 Mile, Morse Creek that are both high in nitrogen and in phosphorus, which definitely kind of sticks out.
Ready to move to the next one?
Yep. And this table right here, we've taken that 2021 data shown in the previous slide, and then we've also combined or added in the 2020 data from the Tributary Blitz that year, as well as the 303D listings, which are it shows which streams have impairments from DEQ. So in this table, I've arranged the tributaries in the same order, upstream to downstream, moving from top to bottom in that left-hand column. And then in each of the years, it shows whether there's a total phosphorus impairment, TP, or total nitrogen, TN, as well as if the stream was assessed by DEQ and which impairments it was found to have. And you can kind of see the same trend as we saw in the previous slide, where those upstream tributaries don't really seem to have impairments. Most of them were not assessed by DEQ, and they did not come back with total phosphorus or total nitrogen impairments from our Tributary Blitz events. And then as you move downstream, we see more impairments. In the summary section, we have the these streams that are highlighted in green are streams that are not found to have impairments, and it kind of all matches up both years as well as the DEQ findings. Yellow is when there's a little bit of, it's not quite consistent. There might be one impairment one year, or it doesn't quite match up with what DEQ has found. And then the red is just showing that it's consistent across both years, across the DEQ impairments. And we have 3 streams that have stood out based on those classifications. We have Moores Creek, South Meadow, and Hot Springs. So those 3 streams are definitely ones that could stand out for possible improvements in the future. And it's important to remember that with these tributary blitz data, it is just a snapshot. It doesn't show a complete comprehensive look at the water quality on these tributaries, but when used in combination with the more extensive 303D listings, it can be a really valuable tool. You can go on, Adam.
Great, thank you, Rhea. Yeah, I think I'm really excited about all the data that the Madison Stream team has collected, and the tributary blitz is I think a really cool way to do monitoring. And while the DEQ can come and do a really detailed and in-depth monitoring assessment when they do it, they're only able to do that every 10 years or so, perhaps, because it's a big state with a lot of streams and limited staff. So in that time between DEQ coming to do these assessments, the local data collection can be such a key way to fill in the gaps and help locals be informed with information about the state of their waters and where to go with projects. So taking a deeper dive into some of the data that has been collected over the years, I'm going to give a little primer on box plots. We're going to see a lot of these, so I just want to give you a quick summary on how to interpret these. If you're not familiar, that center line is the median of the data, and then the box represents 50% of the data points, and the whisker is the highest data point before things that are considered outliers. So an outlier is a data point that is statistically different or notably different based on the distribution of points from the others. So it's kind of hanging out there by itself. At the bottom, we've got this whisker is the lowest point before outliers. In this case, there are no outliers on the low end. But so this is what that data would look like that's behind that box plot. It can end up getting kind of busy, and some of the points might fall on top of one another. So if you plotted just the points, it can be some of the information can be obscured or can be a little trickier to look at. So the box plots are a way to try and simplify that. If this seems like too much to look at, then you can just focus on where the box is, like where the black line is and where the box is. That's where most of the data is at. So that's a box plot reading in a nutshell. And let's jump into looking at some data. So arsenic first to start with. Here is a map of the watershed and each of the sub-watersheds here that have been monitored. And this data is box plots for arsenic. And similar to how Rhea talked about the data being organized, we've got tributaries organized from upstream on the left to downstream on the right, and then within the streams it's upstream to downstream as well in these box plots. So this line is the human health standard for arsenic at 0.01 milligrams per liter, or 10 parts per billion. And just what jumps out right away is that there are a lot of sites that have data above the human health standard for arsenic. So why is that? The Madison is a blue ribbon trout fishery, and it's got really great water quality in a lot of respects, and it's got its headwaters in Yellowstone National Park, which is a protected area. Why is there so much arsenic? And so Yellowstone is the clue there. The concentration of arsenic in the Madison River leaving Yellowstone National Park is 10 times the drinking water standard under most conditions. and that is because of the geothermal activity in Yellowstone. So the Firehole and Gibbon rivers that have that hot water coming up from depth that has dissolved metals carries high concentrations of arsenic out into the river, and then downstream it actually takes until the Missouri River is up on the high line under a lot of circumstances for it to be diluted down to drinking water standards. That means the Gallatins come in, the Jeffersons come in, the Dearborn has come in, all of those rivers before the water gets diluted down to drinking water standards. So if we look at, and we can see, if we put the geology over this, so these tributaries have these downstream sites. We're gonna dive in here on this. The red is the alluvial deposits. That this is in the valleys where the river has deposited rock along its banks, that rounded river rock and sediment layers that make up the floodplains. So this is that red, and that's going to be a big part of understanding this here. If we look at the example of Blaine Spring Creek here, and we zoom in, we've got these two sites up at the hatchery, near the hatchery, and then we move downstream to the AR and then DA sites, and it's that last site downstream where the concentration of arsenic jumps up. And it's down in that alluvial material that is deposited from the Madison River with that high arsenic, and we can see that jump up is correlated to a jump up in flow here. So the way I interpret this is that as you get down to that bottom site, water from the river is coming under the ground surface, springing up into Blaine Spring Creek, and is bringing that high arsenic water from the Madison River into Blaine Spring. And so it's this natural source of arsenic from Yellowstone that is contributing to that high arsenic at the downstream site. In contrast, if we look at Odell Creek, we can see that it starts high in arsenic and then decreases moving downstream. But so if we look at its path in relation to this alluvial Madison River geology, it springs up in that alluvial geology, which is high in arsenic. And then as it flows downstream, you've got these side tributaries coming off of the mountains, off of the Madisons, that are not influenced by that Yellowstone arsenic and have low arsenic and are diluting Odell Creek as you move downstream. So the same natural source of arsenic playing out in two different ways here with dilution. So you can see here that the flow increases moving downstream. In this case, the increase in flow is from that fresh water off the sides of the valley. So moving on to total phosphorus. So that is with arsenic talking about natural sources, and again, needing to understand the natural sources before we can move into thinking about the human sources. So an example of a natural contaminant in the form of arsenic, then moving into nutrients where it's more human sources that we can think about. So total phosphorus, we see this pattern of increasing concentrations moving downstream. That's pretty common a lot of times, where you go from maybe a forest high catchment area to where you don't have a lot of human land use or intensive land use, and then you move downstream to places where we tend to have more people living and are growing more food, and so are using more nutrients. Similarly, for total nitrogen, we see the same pattern for the meadow creeks, and to some extent at the bottom end of Jack Creek. We also have these outliers that are up higher on Jack Creek that we'll focus on in a minute. But here for Blaine Spring Creek, we see this decrease moving downstream. And so what is that about? I think that the same dilution that we were talking about, the same Madison main stem water coming into Blaine Spring at the bottom, causing an increase in arsenic, is causing this decrease in total nitrogen because the main stem of the Madison is pretty low in nitrogen. So flow is a huge part of understanding water quality, and so I've got that exact same plot with sites that we were just looking at for nutrients with now looking at flow. And you can see, yes, Blaine Spring Creek again jumps up in flow at that bottom end. USGS again is a great source of flow data on the main stem, and so this is the Madison near Cameron, and the blue is last year's data, and the orange is the median data for the period of record for the individual days. And so we can see that base flow, or the time of year outside of runoff, when the river is really fed by groundwater and is at its flat, stable flows, is around 1,000 cubic feet per second. And for context, if we just put 10% of that up here on the tributary flow data, we can see that a few of these sites, the downstream site at Blaine and at Odell, are contributing more than 10% of flow to the Madison, which is useful context for thinking about how likely that tributary is to influence main stem chemistry. Jack Creek here also approaches that at certain points, and then some of the other tributaries are pretty low flows, so less potential to affect the chemistry in the main stem, but still important for refugia for fish and for rearing habitat and broader ecology in those tributaries, even outside the context of their effect on the main stem. So jumping into a few specific streams here, focusing on Moores Creek for a minute. I've got this map where we can see on the overall map Moores Creek watershed highlighted. And we've got a lot of rangeland with a little bit of forest up high, and then we've got obviously some irrigated agriculture that you can see in the circular center pivot areas, and then the town of Ennis here, and before it comes into the Madison down here. So Moores Creek, looking at nutrients, total nitrogen, this 0.3 level that Rhea referred to is the level above which we might expect to start to see nuisance algae growth, algae growing at levels that can cause problems. And so across all the sites from upstream to downstream on Moores Creek, there's opportunities for nitrogen projects, nitrogen improvements. We do have this drop as we move to the very bottom site on Moores Creek, which is interesting. And I do want to point out that all of this data that I'm showing, again, is available in the Data Hub. So this exact same plot that I'm showing you, you can go and see in that Data Hub on the MSU Extension Water Quality website, and click on this and change the variables you're looking at and change the plot types and so on. So that decrease in nitrogen moving down at the bottom site, we've got a big increase in flow. So again, I would interpret that as water from the main stem of the Madison springing into that bottom site down there in the lowland and diluting that nitrogen, because again, nitrogen's low in the main stem. Nitrate, I like to show nitrate when I'm thinking about trying to understand nitrogen, because nitrate is soluble, a soluble form of nitrogen, and tends to indicate nitrogen coming in from groundwater. So if you see nitrate above this 0.1 level, that is high enough that you could expect to start to see nuisance algae growth in a lot of western systems in Montana, at least the mountain streams. And so we can see that, again, this is elevated across the reach of Moores Creek, and even up towards the higher end, there is what looks like a notable source of groundwater-derived nitrogen coming into the stream. And again, a peak in that down here at the Goggins property site. So some opportunities for looking at nitrogen projects, and specifically perhaps thinking about things that are recharging groundwater with nitrogen that's flowing into the stream. And then phosphorus, similarly elevated across the reach, with the center sites having more phosphorus. And so in the discussion, it came up that septic systems recharge groundwater, and nitrate is poorly removed in traditional septic systems. And so with more development on septic, you could expect to see increasing issues with nitrate in the streams that are getting that inflow of groundwater if more septics are installed. So hooking up to centralized water treatment and or advanced septic treatment is a way to think about that, reducing that issue in the future. Moving on to Hot Springs Creek. So in the lower end of the watershed, we can see that highlighted, and here are the sample sites. Again, a lot of rangeland here, which we don't typically think about as important big sources of nitrogen and nitrogen certainly, maybe a little bit more phosphorus with runoff depending, and then we can see a little bit more irrigation and probably agricultural land use here, which are perhaps represent some opportunities. And if we look at the nitrogen plots, we can see that the levels do jump up on the South Fork and certainly by near Sterling to levels indicating some nitrogen project opportunities perhaps, and nitrate, at least in the middle reaches, looks like it could be a groundwater source, which is interesting to think about. Jack Creek, so highlighted here, flowing out of the Madisons with the Big Sky Moonlight area and the headwaters that you can see here, and so Jack Creek flowing down the canyon with a lot of sample sites, and then out to the front where we transition to the lower level with more human land use, including some agricultural production you can see there in the aerial. So total nitrogen is below the thresholds throughout most of the canyon, and then does jump up there at the bottom, mostly still below the threshold, but some samples getting above that level where we might expect to see nuisance algae growth. And we do see increases in flow moving downstream, so seeing an increase in nitrogen with these higher flows means definitely some nitrogen sources coming in, and the nitrate shows that, again, probably a groundwater pathway there. And so this is the time series data for the nitrate. To look at this in a slightly different way, these inverted triangles are over the last 10 or so years of data that you can see. It is the highest concentrations downstream, but notable here are these crosses, which are the South Side Road up here in the canyon. And those higher points are interesting for thinking about more on-site wastewater treatment or human wastewater up there with increasing development. And wintertime has been a little bit of sampling that's been done, which is a time of year where most of the groundwater contributions to a stream can really be honed in on, and you can really expect to see those signals most clearly from groundwater. While we're on Jack Creek, I'm excited to show a little bit of this temperature data that through hard work by Rhea to coordinate these, get all of these past files together from the loggers, and then Megan, a student that's been working with me, Megan Robinson, helped to code this and put it together. We are able to see this air temperature data every hour in gray, and then the hourly water temperature data in blue. And we can see these patterns of increasing in the summer in August, which is a consistent pattern in the last couple of years. Interesting, with more drought conditions, to have lower temperatures, which Rhea had talked to some folks and thought that could be a result of more lower runoff coming out of the mountains and more groundwater. A story there possibly to look into further. But if we look at the peak temperatures being in August, and we think about that with the data plotted by month, it makes sense that this is flow being the lowest, dropping off to base flow by August. And so when the flows in the stream are the lowest, that's when you can expect to have the hottest temperatures. It's also the hot time of year, but the two things in tandem with hot temperatures and low flows are when you can really get those peak temperatures. And that leads us to thinking about what are some of the drivers of stream temperature. So obviously we've got climatic conditions are going to be important. Tributaries that are putting flow into the stream and what the temperature of that tributary water is. Another reason to be thoughtful about tributaries. Groundwater temperature, so if you've got deep groundwater coming in, that tends to be cooler water and can keep streams colder. Internal drivers within the stream system, there's riparian shade, so how much of that sun is able to hit the stream's surface, and is there shading to block that? Hyporheic exchange, so the word hyporheic is to indicate the shallow groundwater that is readily interacting with the stream. So it's coming in and out of the stream on over short distances. And there was a question in the presentation about that, like what causes that? And if you think about a stream moving back and forth across the valley and depositing all these gravel cobbles, it will leave these basically pipelines that get buried of cobble and gravel running down the valley, and that can create like a really fast channel for water to flow down valley. And those hyporheic pathways end up being really important for stream temperature and for nutrient cycling. Channel form, if we think about a stream that's relatively deep and narrow relative to one that is wide and shallow, the wide shallow one's going to be at a lot more risk of getting warm because it's got more area to be hit by the sun and less of a buffer against temperature. Whereas, and if we've got that hyporheic exchange, we've got a larger volume of water that can buffer the stream temperature. So some interesting concepts to think about what controls stream temperature. One more piece of final data here is temperature from Moores Creek. Again, excited to have this data pulled together for the first time, where at this site, just at the head of upstream of Ennis, you've got water temperatures never reaching that threshold of 73 degrees Fahrenheit, which is the hoot owl fishing restriction temperature. Just to put that on as a threshold, not to suggest that hoot owl would be implemented on Moores Creek, but then moving downstream to the confluence site, we did get above that 73 degree threshold, and it's for 3 days in a row is the criteria for hoot owl. So this data that is the darker blue means that those conditions would have triggered hoot owl, just for context. So further downstream there's more flow, but the temperatures also got warmer down there. So just as you're thinking about what kinds of data collection you might like to do in the future, just wanted to provide some of these visualizations on stream and air temperature and how you might think about looking at that or thinking about making measurements. And with that, I'll let Rhea talk here for a second. Oh, I think you're muted, maybe, Rhea.
My bad, thanks. So the Madison Conservation District has been working on finishing their watershed restoration plan. The process began back in 2017 with the former employees at the Madison Conservation District, and it's just been an ongoing process. We're hoping to get it over the finish line this year. A watershed restoration plan, it's a document that is accepted by DEQ, and it creates kind of a comprehensive overview and plan for a watershed and how we want to go about addressing non-point source pollution issues to improve water quality in the watershed. So instead of having a political boundary, it is determined based on the watershed boundary. You can see on the map on the right that the Madison watershed has parts in 3 different counties, as well as Yellowstone National Park, which is the Yellowstone National Park part will be excluded from the watershed restoration plan. But the rest of it, we're trying to create that outline. It's a public document, and we really appreciate public comment or input, any insight that community members have. So if you're interested in being involved in that process or would like to see the document, feel free to reach out to the Madison Conservation District. And that's all on my end, Adam.
That's great. Well, I think we're done. This is a picture of the data hub that shows that there's also photos stored in there, so you can go and re-explore any of this data on the website and look at some photos there as well. And feel free to reach out with questions, and thank you for your time. Thank you, Rhea, for the co-presentation.
Yeah, thank you for putting this together. All right, I'm going to end the recording.